Okay, so the main function, let me hide this bar.
Yeah, there's a hide. Yeah, there it was right there. Hide.
Um, so it's this function here is the strain main. This is essentially the main script which controls every other function. The other functions are within this folder here. So tomorrow or today we'll go how to use them, but basically I'll just talk you through what each chunk of code does. So these are the three main external things that you need to run SQUEEZ. So this is the ISO2 mesh toolbox that you can download from this link here. I have put it in the functions folder, but in case you lose it, like this is and just replace this path with that. The next function that you'll need is the NII toolbox. So this is the nifty image reading. Again, the link is here. So this is the link, and just add it to your path again. And the last one is SQUEEZ, sorry, CPD. So the link is again here. You just have to fill up a form and say who you are, and then it'll give you a link to download it. And then again, just add it to the path here.
And then we have current versions of these, obviously, in this.
Yeah, so in this function, here's CPD, here's ISO2 mesh, and here's NII reading. This is another folder that I'll get to maybe later, but it's just the DICOM to nifty conversion. But yeah, so all of this is currently with us, but in case you want to share the software with someone else, then like, because these are not our code, so I don't feel right in just putting this up on GitHub. So these functions are not on GitHub, but I can give this to you in like a hard disk. So if I go back to this folder, so this initial section of the code is what you will have to edit. Nothing else is just plug and play. You just press the button, it should run everything. But this is where initially you'll have to change things. So the first thing is this info.patient. So there's just a patient name. So whatever your folder name is, so this is currently patient 10, just change that. These are your paths to the data. So home path is essentially the path containing your functions. So currently in my current setup, it's 4D strain. So it's all the functions in this folder. Save path is where you want the variables to be saved. Then it makes this folder. Then segmentation path is where the segmentation files are. Image path is where the image NII files are. And DCM path is where the image DICOM files are. DICOM files, this is only useful if you're working with GE scans. If you're working with any other scan, this is redundant because this is, I use this folder to read the %RR and the gantry spacing.
So you're reading the DICOM headers.
Yes. And so if it's Siemens or Philips or etc., like the headers will be different. So you'll have to accordingly just like manually enter it or do something. But for GE scans, it just needs one image. So both of these, image path and DICOM path, you just need one image. You don't need all of them. You just need all the segmentations. I wouldn't touch this. This is just parameters that work. So this is the ISO. So basically the way it works, it resamples each image to 0.5 isotropic, and then it downsamples it to 2. So ISO resolution is the isotropic resolution. Desired resolution is the resolution that you want the meshes to be, the desired out resolution of the meshes, pixel spacing of the meshes. Averaging threshold is just when you're averaging the matrix to just make it binary. This does not work. We've tried this a bit, but it doesn't work very well. So just keep it 0 for now. So this is a flag. So 0 or 1. These are your segmentation labels. Again, would not mess with this. So this is 1, 2, and 4. This is historically what Davis has set up. So 1 is LV, 2 is LA, 3 is LVOT. For SQUEEZ, we need all 3. So you have, we don't need the full structure, we need the planes. So if you don't have them, you'll get a ventricle with a closed valve plane and a closed LVOT. But we don't have that, we don't do that anymore. So if you want to remove them, you need to have 3 segmentation labels in your IT case line. So this is your desired time frame. So basically, if you have a series from 1 to 20 time frames, but you don't want to analyze 20 time frames, you want to analyze every alternate one. So I will just change this to say 1 in steps of 2 to 20. Or if I just want to analyze end diastole and end systole 1 in 8, or 1 in 10, or whatever. So
But one is always assumed to be the
right.
starting point.
So that is the next part. So the way I have historically done it is I always make my end-diastole in my image NII and my seg NII folders. So basically these folders here. So if I go, so let's just go here. And so image NII, this is the folder structure. This we'll go over this tomorrow, I guess, or whenever. But the way I make this folder is that image_00 is always in diastole.
Okay.
Because others I'll get confused
Yeah.
because I don't know which one's what. So I always keep it end diastole, early systole, end systole, diastasis, back. But if you are more confident in the way you organize your files, you can alter these. So in that case, this will be info.template is the template mesh for registrations. This is what CPD is warping. So say we want diastasis. So I'll make this timeframe 17. So that it will use timeframe 17 as your model now, which it fits. And
As the
template for the displacement field. If you want diastasis again to be the reference for strain calculation, because there are two parts. One is warping, and then it uses a mesh as a template for the ratio of the areas. So that is this info.reference.
Okay.
So that again, if you want it to be in diastasis, make it 17.
Wouldn't they have to change together?
Because one is just finding the displacement field, and then the other is just using a template mesh and like finding,
making a deformation on that mesh. Okay.
This is the flag for Gabi script endocardial strains. So as I mentioned before, basically the default is SQUEEZ. You cannot switch off SQUEEZ. It will calculate SQUEEZ. But if you also want ECC and ELL, turn this to 1.
Okay.
This is a little more time consuming than SQUEEZ. I think each time frame takes a couple of minutes at least. So, you know, it's not, so unless you really want it, I would keep it off. So this is just a check. Basically, it's just saying, so there's a for low pass filter for the mesh points, which is the smoothing operation, the temporal regularization. Essentially, I have just kept this as a check such that if I forget to switch this on or off, because this is the flag info.smooth words. So it's basically smoothing vertices positions across time. And if this is 0, it won't smooth it. It'll just give you the unsmoothed mesh. If this is 1, it'll do the low pass filter. But this should be on only if you have a periodic cycle.
Okay.
So if you're just running end systole and some 3 time frames, you shouldn't. It should be periodic. So that's what this check is.
Annotate that up at the comment about timeframes, info timeframes.
Okay.
Or annotate it down below at the verbs.
So I have it here.
Yeah.
Flag for temporally smoothing CPD vertices using Fourier decomposition. Use only when there is one complete period.
I see. Okay. And so this is the expansion of it in Fourier terms?
Yeah, exactly.
Right.
Exactly.
Okay.
So it's expanding it, and right now I just take the first 3 harmonics.
Got it. Got it.
So this is just a flag for most of our data sets. It's periodic, so it is usually 1 unless we're like trying to analyze something differently. But it'll just give you this as a check, and I just put 5 as a limiting threshold because I'm like, there's no full period which is less than 5 time frames.
Okay.
But there's just
less than 5. You say something weird is happening.
Yeah, it just throws an error.
Okay.
Yeah, so this is the only part where you'll have to change things.
And you change each of these for each patient you do.
Exactly. So right now it's not batch processing. It's each patient you have to do it. I forgot to mention this section here. I commented it out because this is the GitHub code. So this is where it works for GE scans. And I've said that here, finding %RR and time between frames works only for GE scans. For other manufacturers, have to change the corresponding DICOM tags.
Right.
And this is the function here, timing info. So it essentially just takes in the path, goes into the DICOM images, and it reads the gantry interval, it reads the time between frames, and it reads the percent RR.
Oh, that function timing info. does
This
that.
timing
Yeah,
info,
okay.
yep. And then it'll display those three. It'll say percent RR so and so, gantry difference so and so, time number of time frames so and so.
Mhm.
So for G scans, it works perfectly fine. Other scans, you have to. I haven't tested it for other scans, so.
How did we do it on the AOH data then? Because they're not GE scans.
AUH data, we went into Cyrix and we essentially did that, I think. Horrors, as far as I remember.
Okay. And when did you run this for the AOH
Mhm.
stuff, right?
Mhm.
And so you then at this point
I just commented it out.
commented it
Yeah.
out and just set.
Yeah, I commented it out, and then there's a place here where you can manually enter it.
Got it.
So I'll come to that. But so if it doesn't read that there, it'll read it here, and you can override it by having it here explicitly. So this is the first section. So this is basically all that you need to do to set up. And once you set up, then it'll just like say analysis parameter saved and whatever. And this is the main image processing function. So if I open this, so this is the image processing script. So this is the biggest script in the code. But essentially what it does, if I just go through blocks, so the first block is this. So this is just reading the data. This is reading the segmentation file. So each NII, it's going in and reading the segmentation file. Then it prepares it. So it essentially extracts the LV, the LA, and the LVOT. And then because it's a Nifty, the direction matrix is different from our traditional DICOM viewing. So it just kind of transfers it back to traditional like DICOM direction matrix. Then it makes it isotropic. So now it takes in whatever the native resolution is. So if it's 0.625 by 0.4 by 0.4, it makes it isotropic such that it's 0.5 by 0.5 by 0.5. And this is a loop. So it's doing this for every single segmentation file.
Okay, and the segmentation files, remind me again, they are binary inside the LV volume across the whole thing. They're binary with different numbers for the LAA and the aorta.
Yeah.
Okay.
So they're just categorical matrices with 1, 2, and 4. Or if you run the CNN, you'll have more labels, but it'll just extract 1, 2, and 4. It doesn't extract anything else. So you can't use, meaning if you want to do RV function, you'll have to change these labels here.
So data image info.lv. Oh, I see. So that just defines what the value is.
Yeah, so I initialize a matrix, the size of the image with just zeros. And then I say within the image, all the voxels which are equal to LV label, make it 1. And all the voxels which are equal to the left atrium's label, make it 2. All the voxels which are equal to the LVOT's label, make it 4.
So it's just taking the NI, making it a value.
So now it's just an array. Yeah. And these labels are defined in this function here that we went over. So these. So you could change them but we've always made it 1, 2, and 4. So I'll just stick with that. But so then it puts it changes the direction matrix. It puts it into the format that we're familiar with. Then it makes it isotropic. So now it's 0.5 by 0.5 by 0.5 at this stage. Then it calculates the LV volumes across time. So this is just basically info.vol. I'll go over when we run the squeeze code, I'll show you all the outputs. So essentially you'll have two main variables. You'll have this info variable, which is nothing but it's treated exactly like the metadata. So it's just a structure with many fields that are just like the information fields. There's nothing you can compute, but it's just things that you need to know. So like all the parts, the labels, like volume, etc., is all stored in this info. The other main variable where it all has the meshes, the squeeze values is mesh. So the main two output variables are just mesh and info. So now info.volume is stored here. So I've tried my best to comment each section, each block, but I know it's kind of very difficult to understand someone else's code. But This is info.fill paps. This is when you were trying to use the convex hull and try to kind of take the negative of the paps. It doesn't really work, but this is the flag that I showed you here, info.fill paps. I would just leave it as 0. But if you want to explore that, basically,
Yeah, sure.
It just runs this here. So this is the process where it takes it, makes the convex hull, finds this negative, subtracts the paps, and then removes the paps and makes it like another volume.
Okay.
It doesn't really work, so I would not.
So that's basically shut off.
Yeah, this section is shut off. I didn't delete it because if in case someone wants to improve on it, yeah. But this section just does the pap removal. So then this is the next part. So now the only user input that you need after you initialize those paths and everything is defining the axes.
And
And
the long axis and the
so there are 3 rotations which are performed. One is basically, so if the ventricle is oblique like this, right? So one is this rotation, the second is this rotation, and the third is the rotation in this such that it goes into proper AHA coordinates. So that is what this section does. So essentially, it'll throw up an image for the user and you just click the axis. Like you just click one here, then it'll pop the second image, you click one here, then it'll pop the short axis image up where you just click inferior and anterior wall. So it knows those 3 and it just stores those values. It doesn't rotate anything now. It rotates only the meshes. The images are never rotated because they're it's a time consuming process.
So this is basically an interactive portion of the code.
Yes.
Collecting these data.
Yep.
Okay.
So it takes the NII. This is why you need the NII image, because
that one image.
Right. So that so that you have the RV, because otherwise it becomes difficult to decide where the anterior and the inferior wall is. So it takes the NII image, it crops it such that the rotation is more efficient, and then it just basically like does that. So it just crops it and then rotates one angle. So this is the Z rotation, then rotates X rotation, and then rotates the last orientation, which I call Y. It's not actually Y, it's about Z, but I just wanted to differentiate them. So it's Z, X, and Z again. So these are the 3 rotations, and then it just deletes all of them and just stores those values in, again, the info variable.
Okay.
So info.theta Y, info.theta X, and info.theta Z, all of these are in radians.
Okay.
So that is the interactive.
They have to be done in that order.
They don't have to, but like you can't get the short axis until you put it in one angle. So, and this is the downsampling now. So this is same from Amir's code. This is the section that I haven't changed, where he just defines an averaging filter and just picks. So he averages in steps of whatever the desired resolution that you want. So the way now it's coded is 0.5 is the native resolution that it kind of first resamples it to. And then from 0.5, we have stuck with 2. Okay. So that's steps of 4. 2 divided by 0.5 is 4. So it just basically takes an averaging filter of a 4 by 4 and of 5 by 5 by 5, and then just goes over the image and just averages it and then picks out every 4th voxel. So that is this section here. So this is defining the averaging filter. This is downsampling the LV. So this is exactly what I just explained. So it's using the IM filter. It's using this IMLV, which is this FF, which is the filter here, and symmetric. And then it picks out. So 1 in steps of whatever the step is, which is now 4 to the end, 1 in steps of 4 to the end, 1 in steps of 4 to the end in the 3 directions, X, Y, and Z.
Does this use intrinsic MATLAB functions for doing the downsampling, or is this just written out like it's Fortran code?
This picking is written out as Fortran code. The filter is an intrinsic MATLAB function. Okay. IM filter is the function that MATLAB is doing to blur the image matrix. Right. So this is for the LV. Now, because we have the mitral valve and the LVOT, we have to do that for that as well. Okay. So identifying largest. So this is identifying largest connected component for LV. So essentially, if there are small like little voxels out here and there, just kind of cleans it up. So that's what this section does. This section, largest component and downsampling LA. This is exactly what was done for the LV, but now for the left atrium. So that is this section here. And similarly, exactly to the previous two sections, we do the same thing for the LVOT. So this is label 2 here, this is label 4, and the LV was label 1. So it's just doing it for those 3 labels, and now such that everything is in order and downsampled to 2 millimeters. And now this is the section that picks out the valve planes so that we can delete those points in the mesh. So the first thing is dilating. So it's just basically a bunch of dilation and erosion operations. So dilate the LV, see where it crosses the mitral valve, dilate the LV, see where it crosses the left ventricular outflow tract, identify those indices, because those indices are directly translated to mesh points. When you make the mesh, each voxel becomes a mesh point. So what this chunk of code does is essentially it finds those voxels that are the boundaries, that are the planes, and stores those values. And then when we actually go into extracting the mesh, it kicks those out. Okay. So this is the dilation operation here. So it's again using an intrinsic MATLAB function, IM dilate, IMLVOT is the image, and this is the filter that I choose. It's just a ones. It's just a box, yeah. Then this is identifying the coordinates. So essentially I'm adding these two. So where I'm saying IMLV dilate, which is this, plus IMLA, which is the non-dilated image of the left atrium. Wherever that's 2, find that and store it here. And similarly, wherever IMLV dilate plus LVOT is 2, store it here. So M is for mitral valve, L is for LVOT, and this B is the band of tissue. So it's basically the trigonal section. So sometimes the ventricle, there's a gap between the LVOT and the LA. So this, I just call it a bridge. Okay. I don't know. I don't know if that makes sense. So if the LVOT is going this way, the LA is here. There's a chunk of the valve which kind of doesn't belong to either of them, but it should be kicked out as well. So that is this section here. And that depends on how the person segments it sometimes. So if the mitral valve plane is a little higher, then you'll have that band. Okay. If it's lower, you won't have the band. But it's just a check because sometimes it kind of creeps in. So this is again the same thing. So now it's using where the LA is dilated and the LVOT is dilated and finding that intersection here and then storing those indices here, those coordinates. This is the mesh extraction. So this is again an intrinsic MATLAB function isosurface. And then it just saves mesh.faces. So this is the first place where mesh crops up. So these are the faces. So there's the connectivity matrix. And this is mesh.vertices. So these are the indices for each mesh point. Sorry, not indices, coordinates. And then this section is where I'm kicking those out. So I'm finding those points in the vertices that we identified here as the indices in the image space. And once I find those, I'm just kind of finding the indices that belong to those planes. And essentially, this is all just processing steps here. And here, I think I just kick them out here, nanning out here. This is the final step. So this whole section here is just finding those points. The ones that we dilated in image space and translating that to the mesh coordinates such that that intersection corresponds to the certain mesh points here, finding those mesh points and removing them. And that is done this final step here. So just making them nans essentially. So again, I kind of commented them out, but I understand it could be kind of weird.
Sometimes when you read the comments, oftentimes general terms are used, like now we will change the rotation, and you're like, what rotation? So any general noun that you see in the comments, you should try and specify it, like what is particular, about that noun, like which rotation we're talking about, which boundary are we talking about, right, and it keeps that flow. Because without a diagram, it gets very complicated, right? To try and figure out what's going on.
Yeah, no, for sure. So let me know if I can go back and re-comment some. But this chunk of code essentially says extracting faces belonging to all the vertices. So each vertex has usually 5 faces that it's connected to. So each vertex, I'm getting that connectivity matrix out here. And then I'm isolating the disconnected meshes. The reason I'm doing that is because those are the chunks here which are belonging to the objects that I don't want.
I see.
So this is part of the ISO2 mesh toolbox, find disconnected surfaces, and it removes all of that. So it's kind of a cleaning operation. So analogous to in the image space where you just find the largest connected component, in mesh space, it's just finding out meshes which are not part of the main object. Exactly. And then choosing the object with the largest number of faces. This is because I want the LV. Extracting the vertices corresponding to those faces.
Okay.
To those faces of the LV. So I can maybe say that corresponding to faces of largest component is LV. So that is this section here. And then everything else that we didn't disconnect, I'm just going to make it NaN, because those are not important to me. So by doing this, now I've kicked out the LVOT, I've kicked out the mitral valve, I just have the left ventricle endocardial surface now. If that makes sense.
Okay.
This is just identifying limits for plotting because each ventricle is different. So I just center it. So again, you don't need to touch this. It's just finding limits. It's like, okay, what is the maximum Z limit? Put some tolerance. Minimum Z limit, put some tolerance. Maximum X, put some tolerance. That's it. So it's just a very simple operation here. And that's it. So this is one loop for one time frame. So all of this happens for each segmentation file. And then it's all stored in this and this.
But each segmentation file for each time frame has its own mesh file.
Yes.
I see. So you're going to have multiple mesh files.
Yes. No, not multiple mesh files. It's one mesh file. Sorry, I misunderstood. So I'll just pull up. So that's it. This is your output from SQUEEZ.
I see. So
just 13 time frames.
Time frames are in mesh.
Yeah. So these are each. So mesh has all these fields. And we can go over this when we run the code, but so these are your faces, vertices. These are the indices for the mitral valve plane, LVOT, the band that I was talking about. Crop what? So the vertices that are cropped. So basically it's just the LVOT and not the mitral valve and the LVOT. CPD without smoothing because we are testing this for the TAVR thing. This is a correspondence matrix of CPD and so on. But I don't want to mix things up. We can go over this when you run it.
Got it.
So this is the main image processing function.
And that gets us to the point now.
That's
here. Have these meshes defined that and cleaned and everything for each time frame. And so now you could actually just make a video of that. Those meshes. Take a look and say that is the data which we are going to process. Okay. So up to this point, we haven't. It wasn't necessary really to just define who is the 0 time frame or anything like that. This is just getting in raw data, cleaning it up, making into meshes that are now sensible. Right.
The only thing, I guess, one definition that it takes is for the rotation here. It chooses just the one because it chooses the template. It needs one image. So essentially your image NII has to be the template image. So if you choose 17, make sure that you choose 17 in that flag.
As your first orientation thing. Otherwise there could be some weird shift.
Otherwise it just won't read it. Because it just says only do it for that time frame. So time frame of J is equal to info.template, then throw up the rotation matrix, because template is what I always thought is going to be the largest volume. So then you can get the angles the best. That is my logic. But that's the only information that you need. Otherwise, it just treats it as numbers. Like this section just treats it as like individual time frames. So
why don't we pause here before going to the next section, and you can pause your recording probably. And you can